Let's take a look at problem A. Guess the maximum. We are given an array of n integers and we have to find an integer k such that for any subarray of at least length 2, the maximum of that subarray is strictly greater than k. Now one thing you have to notice is that the only subarrays of our concern is when j is equal to I plus 1, that is when the subarray has length 2 and has only ai and ai plus 1. We simply have to find the lowest of the maximum of these values, and k will just be 1 less than this lowest maximum. So now let me walk you through the code. Over here we are just reading the inputs. Then I initialize my lowest maximum to be the max of a0 and a1. Then we find the maximum of ai and ai plus 1, and lowest maximum is simply the minimum value of this. Finally, k is simply 1 less than the lowest maximum, and we output that.
Hello, this is Kashyap. Now, moving on to the B question, XOR sequences, we are given two integers x and y, and for this, there are correspondingly two infinite sequences ai and bi, and in which an is equal to n XOR x and bn is equal to n XOR y, which is bitwise XOR. And for this, we have to look at two subsequences of a and b each, such that the corresponding elements of this are equal. That is, the length of the subsequences are same, and they have said that if there is I and j such that ai is equal to bj, ai plus 1 is equal to bj plus 1, and so on till ai plus m minus 1 is equal to bj plus m minus 1 of length m. We need to input this maximum m that is possible. For this, let's look at how x and y can be looked at. For this, let's divide x and y such that the first few bits starting from the least significant bit of x and y are identical. All of the bits are identical, starting with ith bit being different in both of them, after which we call them as xd and yd. Before that, let's call them as xs and ys. So, as the sequences are A and B, we have X XOR A and Y XOR B are equal. As this is bitwise XOR, we can just equate the individual bits, and for this, let's take only the different bits. For this, XD XOR AD and YD XOR BD are equal. And as XD and YD are different, we can't really like find the values of AD and BD. They depend on the values of XD and YD. So we are restricting those values. On the other hand, if we look at XS and YS, XS XOR AS and YS XOR BS are equal, but XS and YS are identical. So in this case, as it is XOR operation, we can just say AS is equal to BS. And we have seen that this is independent of XS and YS. So as AAD and BD have a restriction and AS and BS does not have a restriction, we can just set AS and BS to whatever value we can put as long as AS is equal to BS. So for this, the number of values is equal to 2 power s, where there is s bits. Now we can also note that if there is an equal value in the xd and yd part, that is two bits are identical over there, we can think that maybe that can also be added as a variation in a and b values. But if it is disconnected from this AS and BS, then it will be in a different place than this. That is, it is not lying in this subsequence, they are discrete. So we are taking only the continuous values from the least significant bit, which is equal to 2 power s. Looking at the code, we see that we are taking in inputs x and y, and I am using a for loop for this, a standard for loop, so that it is easy to understand. We can also do this using bit set. Now for this, we are seeing if the last remainder with 2 is same for them, that is the least significant bit is equal or not. If it is equal, we are just dividing them by 2 to find the next bit. If it is not equal at some point, then we are using the ith value into a variable power and then breaking the loop, and then we just have to find 2 power this value of power. And for this, we are using a loop for loop to multiply answer by 2 power times, and then we are just outputting the answer, and that is this question solved. Now moving on to the C question, this says that there is a game in which there are n outcomes. For each outcome, there is a corresponding value ki such that, let's say we are betting amount of si in the ith outcome, then our outcome is ki times si. That is, the profit is ki times si. Now the constraint on this is that for all the values of I, ki times si should be greater than the sum of si values, that is sigma si for all I is equal to 1 to n. And this should satisfy for all of the values of I. So for this, let's look at the notes. Let's see why all of the ki and si values should be the same or nearly the same. Let's say one of the values is greater than the remaining other values. In this case, we can just reduce the value of coins that we bet on that outcome to get the value down. Or if it is less, we can add a few more to get that value up. If it is more, we are getting it down and we are reducing our budget and favoring the other ki values. If it is less, we are increasing the coins so that we are favoring that outcome by not having that break the loop. So now we have seen that they should be ideally the equal amount so that all of them can be uh, at the same time greater than the sum of our values that we have used. Ideally, they should be the same values. And in this case, we can just take ideality and KISI should be equal to K1S1 is equal to K2S2 is equal to K3S3 and so on is equal to KNSN. So for this, we have seen that this total value that we have gotten is divisible by all of the KI values. And SI is up to us to choose. So we can just say that this total value is the LCM of all KIs. And the given constraints are small. That is, they have given that n is less than 50 and k is from 2 to 20. So for this, it is pretty simple to find the LCM under the given time limit. So we can just find the LCM of all of these ki values, and that will be our total value for each winning outcome. And so the SI value will be just be equal to this LCM divided by KI. So what the constraint now we have is the sum of values, that is sigma of SI, that is sigma of LCM by KI. If it is less than the total LCM value, then this is our winning outcome. So we just print all of the corresponding SI values, that is the corresponding LCM by KI values. If not, if sigma SI is greater or equal to LCM, this means that it is our budget is greater than the winning outcome, which is unfavorable. So we just print -1, that it is not possible to find such a case as we are using the most ideal case. So this is the logic, and looking at the code, we are taking n as input and taking all the k and ki values as input. Now for this, we are running a loop from 0 to n-1 to find the LCM of all the values of ki, and then another loop to find the total sum of all values of si. Si is LCM by ki. So yes, now this is our if LCM value is less than or equal to sum, that is sum is greater, this is unfavorable, so we print -1 and return the function. If not, then we know that it is the winning outcome, and then for all the values I is equal to 0 to n-1, we print out si values, that is we print out LCM by ki values correspondingly. And that is this question solved. Thank you.
Okay, now let's look at D, fixing a binary string. In this question, they've given us a string S consisting of zeros and ones, and they've also defined an operation as follows. Basically, we can choose an integer p, take the first p characters of our string, reverse it, and move it to the end. They've also called a string k proper if every partition of length k is of the same character, and also consecutive partitions are of different characters.
Okay, to help you understand better, I will provide an example. Let us say n is equal to 4 and k is equal to 2. Then there exist only two possible k proper strings, either 1100 or 0011. In fact, like for any input string s and k, there is only two k proper strings. Okay, now I actually know how to solve this. I'll simply brute force for every p. I'll apply this operation and check if it is equal to one of the k proper strings.
Hmm. But but if you go through every single P, you will need to do an ON operation to check if the transform string is valid. And since P can have n values, wouldn't this have a time complexity of ON square?
Hmm, that is true, but I was recently reading an article on string hashing, and what this allows us to do is perform this operation in constant time, that is in O of 1, and this immensely speeds up a solution. Now, the gist of string hashing is essentially that any string can be encoded as a polynomial in some prime p modulo some other prime m. Now, let us take a look at how to implement this. Now, you might notice this line uh, using z equal to mod int a prime number. This is just a helper for me to perform modular arithmetic. I will provide the source for this in the description. We are reading the inputs over here. Now, since we have already concluded that there are only two possible k-proper strings, I calculate the possible k-proper string either starting with 1 or starting with 0. After this, I create two arrays, prefix hash and suffix hash. The ith element of prefix hash contains the hash of the input string up to the ith character, and suffix hash it is the contains the hash of the input string but in a reversed. Now we come to the meat of the solution, where we apply the operation for every p and calculate the hash of the transform string. Now you can notice that the string is essentially made up of two parts, the substring from p plus 1 to n and the reverse substring from p to s1. To calculate the hash from p plus 1 to n, we can notice that the string hash essentially is like a polynomial. So to calculate the hash from p plus 1 to n, we simply discard the elements from 1 to p and divide the polynomial by p power I plus 1, which is what I have done over here. To calculate the hash for the second part, that is the substring from p to s1, notice that this would simply be the hash if the string were reversed. Now the complete hash would just be the summation of start hash and end hash, since both of them are just polynomials in P. Once we have the hash of the transform string, we can compare it with the hash of the two k-proper substrings. If they match, it means that applying this operation at P does give us a k-proper string, hence we can output that. If after iterating through every possible P, we have not found anything where the transform string is one of the two k-proper substrings, then we output -1.
Hello, I'm Raadhes, a club strategist at the Programming Club IITM. So I'll be giving the editorial for problem E in yesterday's contest. So I hope you read the problem. So basically, the problem statement is that there are n points given and we are to find a triangle such that the distance between every two points is distance d, and the distance between two different points is defined as this. So it's not normal distance. It's called Manhattan distance here, and this is definition. So it's basically the sum of absolute differences in the coordinates. So I'll be giving you my approach to this problem. It's pretty similar to the one given in the editorial. So this is my approach. So the first thing that we can observe is that there are always 2 points in such a triangle which are on a 135 degree or 45-degree line with the horizontal. So I'll give you a simple case first. Suppose we have point P. Then the other 2 points must lie on this square. That is the set of all points which are distance D from the point P. So suppose that second point Q is on this point, is here. Then the third point has two possibilities, R1 and R2. And you can observe that you can find in the first triangle PQR1, P and R1 are 135-degree line, and R1 and Q are also on 45-degree line. So here there is no problem. You can always find 2 points on the triangle which are on 45 or 135-degree line. Suppose Q was a bit somewhere else. What if it was here? If Q was here, then we have two cases for the third point. Third point can be here or here. Suppose we take PQR1, then P and R1 are on 135-degree line. If we take the other case, PQR2, then Q and R2 are on 135-degree line. Let's see one more case. Suppose we moved Q even more this side. Here, in the first triangle, PQR1, R1 and Q are on 135-degree line, and in this other one, P and R2 are on 135-degree line. So like this, you can kind of convince yourself that there's always 2 points in such a triangle which are on 45-degree or 135-degree line. Now let's go into the mathematics a bit more. I mean, it's not hard mathematics, but yeah. Okay. So case 1. Suppose that the triangle contains 2 points on 135-degree line. That is a downward sloping line. So now we take every point P. So there are n points given to us. We choose P to be every point and check one by one if such a P will satisfy. How do we check? So suppose P is this, then what is Q? So Q has to be on the same 135-degree line, which is a line of this format, x plus y equal to k, and its Manhattan distance from P is d. So these would be the coordinates, given that the coordinates of P are this. Now, how do we choose the last point R? So it turns out it must lie on 2 lines. It can lie on 2 lines. So the first case is x plus y equal to k plus d. R can lie here, so these are different points which can be R. And or R can lie on x plus y equal to k minus d. This is the second possibility. Also note that R must also lie between these 2 points. You can kind of get an intuition. If R lies further ahead than this, then the distance from P will become too high. So if you do the calculation, you get the different coordinates as this. So if R lies on x plus y equal to k plus d, its x coordinate must be between x1 and x1 plus d by 2, where x1 is the x coordinate of P. And note that here the x coordinate of P is less than q, and we can assume that without loss of generality. Now if R lies on the bottom line, then its x coordinate must be between x1 minus d to x1 minus d by 2. So this is all the math behind it. So how do we solve the problem after getting this? So what we can do is we can distribute all the points into sets, and not sets, you can put it in vectors also. So you just put them into different vectors such that each vector represents a different line, a different x plus y equal to k line. And then what you do is, for every point P, you find if there exists such a Q in the same set, such that its x coordinate is this. If it exists, then good, we can continue. If it doesn't exist, we move on to the next point P. If it exists, what we do is we go to the sets corresponding to k plus d and k minus d. So in k plus d, we have to check if there is a point with an x coordinate between x1 plus d by 2 and x1. We can check this very simply using binary search. So what you can do is, you can use a lower bound function on the vector after sorting it. and check if there is a point which has greater than or equal to x coordinate x1. And once you get such a point, you check if it is less than x1 plus b by 2. If it's not, that means that there is no point between these two. So it's simple binary search. And to find q also, you would use a similar binary search. And you can do the same thing with the x plus y equal to k minus d line. This was the case when we had 2 points on 135-degree line. So the other case would be when 2 points are on a 45-degree line. So on 135-degree line, what we did was we separated points into sets where each set had the same value of x plus y. Here we would separate points based on x minus y. And after that, everything else would be very similar. It's basically kind of mirroring on the y-axis, kind of like that. So yeah. So you can try coding this up by yourself. If you have any doubts, you can check out any grandmaster's code, anyone else's code is solved. You can check out my code as well. My code might be a bit different because I did based on the y coordinate, but that shouldn't be a big difference. So yeah. That's it for today's editorial of problem E. Do like our video and subscribe to our channel and keep on giving Codeforces contests. Thank you.